आता लेक्चर घेत आहे सर मी. Neeraj sir, please. Okay, thank you, Neeraj sir. Welcome, student. Welcome you all in All India Council for Technical Education AICT New Delhi sponsored Prerna scheme. Myself, Mr. Asif Beg, Assistant Professor, Civil Engineering Department, Tulsiramji Gaikwad Patil College of Engineering and Technology, an autonomous institute and accredited NAC accredited with A+ grade. So, student, today we will discuss on the topic that is hydrology, in which we will study the hydrologic cycle, precipitation, evaporation, evapotranspiration, watershed, infiltration, and unit hydrograph. So, what is the definition of hydrology? What is hydrology? Hydrology is nothing but a science of occurrence, movement, and distribution of water above or below the land surface or in the atmosphere. So, on the basis of this definition, we can divide this hydrology into two, that is surface water hydrology and the groundwater hydrology. So, we will first see about the surface water hydrology, and then we will move to the second, that is groundwater hydrology, in the next class. Okay. So, in the surface hydrology, the very first term, that is the catchment area, we will see. So what is mean by the catchment area? It is the area of the land which is draining into the stream or a water course at a given location is known as the catchment area. So you can see here in the diagram, this line is nothing but the catchment area. Okay, so I'm just using the red pen over here. So this this M station is nothing but the catchment area, and this river A is passing through this. Okay, so this outer line is nothing but the watershed divided. Okay, and this river is passing through this M station. Okay, so this is nothing but the catchment area. So another example you can see here. This is the topographical view of the catchment area, in which the river, which is shown in the yellow line, shown here, and this green portion or yellow shaded portion is nothing but the catchment area over this. Okay, so this yellow line is nothing but the river, and this green shade shows the dimension in meter, that is 949, 787, 627. This is 140. So this is the catchment, the area, or the distance of that particular catchment area into the meters. Okay. Now, what is the equation of water budget? So, from the continuity equation for water, that continuity equation we have learned in the fluid mechanics subject, that is the mass inflow minus mass outflow is equals to change in mass storage. So, on the basis of the principle of conservation of the mass, this water or the continuity equation has been formed, and from this continuity equation we have to calculate the water budget equation, and that water budget equation of the catchment area for a time interval delta t is written as P minus R minus G minus E minus T, that is equals to del S, where del S is nothing but the change in storage, and P is denoted as precipitation, R is nothing but the surface runoff, G is nothing but the net ground water flow out of the catchment, E is nothing but the evaporation, and T is the transpiration. Okay, so all these terms in the equation may have the dimension of volume or depth over the catchment area. So this is what the equation we have to use to calculate the water budget, del S. Okay, so when the in the gate examination you have to ask to calculate the change in the storage, del S, so you have to use this equation, and on the basis of this equation we will have some solved numerical which is asked in the gate examination, and that we will see after the this topic covered in the presentation form. Okay, now these are the type of example which is might be asked in the gate examination. So just I am taking these questions here, and we will solve these questions after the class. Okay, the same type of question is asked in the gate examination as well. So the question is asked as a lake had a water surface elevation of 103.2 meter above the datum at the beginning of the certain month. So in that month, the lake received an average inflow of 6 meter cube per second from surface runoff sources. So in the same period, the outflow from the lake and the average value of 6.5 meter cube per second. So further in that month, the lake received a rainfall of 145 mm and the evaporation from the lake surface was estimated as 6.10 centimeter. So write a water budget equation for the lake and calculate water surface elevation of the lake at the end of the month. So the average lake surface area can be taken as 5,000 hectares, and we have to assume that there is no contribution to or from the groundwater storage. So this is the one of the type of question which is asked regarding to calculate the water budget equation, and all the rest of the things P, R, G, E, and T are given in the question itself. Now, another example is asked about the catchment area, which is given as 150 hectare and which receives a rainfall of 10.5 centimeter and 90-minute duration due to a storm at the outlet of the catchment. The stream draining the catchment was dry before the storm and experienced a runoff lasting for 10 hours with an average value of 2 meter cube per second. So the stream was again dry after the runoff event. What is the amount of water which was not available to run off due to the combined effect of the infiltration, evaporation, and transpiration? So also we have to calculate the ratio of the runoff of the precipitation. So in this case, rest of the values are given and we have to calculate the infiltration, evaporation, and transpiration. So sometime it is to be asked in the examination to calculate the change in the storage. Sometime it is to be asked in the examination to calculate the evaporation, transpiration, and any other parameter which is given in the equation. So we have to use this equation to calculate not only to calculate the water budget equation but to calculate the precipitation, surface runoff, net ground water flow out of the catchment, evaporation, or as well as the transpiration. Okay. Now, after having the equation of water budget, we having the annual world water budget. Okay. So you can see here, this is the what we can say graphical representation of the water which is present in three conditions, or we can say locations. So oceans is having 1.35 350 into 10 raised to the power 15 meter cube of water. Okay. Now in the evaporation per year, the water is evaporated from water is 361 into 10 raised to the power 12 meter cube per year, and through precipitation, the amount of water received in the ocean through atmosphere is 324 into 10 raised to the power 12 meter cube per year. So whatever the value is evaporated, so less amount of water is received through the precipitation in ocean. Okay, so atmosphere is having 0.013 into 10 raised to the power 15 meter cube of water, and that is to be precipitated in ocean as well as on land. So you can see here in the figure, the precipitation in ocean is 324 into 10 raised to the 12 meter cube per year, and precipitation in on land is given as 99 into 10 raised to the power 12 meter cube per year. Okay, so through land, the atmosphere receives through evaporation or by transpiration, that is the amount 62 into 10 raised to the power 12 meter cube per year, and land is having the water 33.6 into 10 raised to the power 15 meter cube. Okay, so this is what we have the annual world water budget through this graphical representation. So this is the very clear picture that what amount of water is evaporated through ocean, what amount of water evaporated through land, and what amount of water is precipitated through atmosphere in ocean as well as on land. Okay. Now you can see here in the another graphical representation, the hydrological cycle is given. So in the hydrological cycle, the amount of ocean water is given as 1370, that is equal to this amount. Okay, so here the amount is given as 1350, so plus minus 20 into 10 to the 15 meter cube is there. Okay, so you can see here the evaporation is done. Sorry, so evaporation you can see here. Okay, and this due to this evaporation, the cloud is formed, and then after getting this cloud warmer, the precipitation is happening. Okay, now the ocean water is increases not only because of this precipitation only, but because of the land water which is what we can say flow through the river and go to meet with in the ocean. So you can see here the precipitation which receives on the land that goes in the river, and river through this river this meet with this ocean. Okay, so this is how this precipitation and evaporation process is done. Okay, now on the land you can see here the evaporation as well as the transpiration is done. Okay, so transpiration is nothing but the water evaporated from the trees. Okay, and it goes to the atmosphere, and through that atmosphere uh, uh, in the form of precipitation, the again this land receives the water. Okay, so this is what the cycle of hydrology you can see here. Okay, now, what are the types of precipitation? So, first type of precipitation we have, that is cyclonic precipitation, when air masses rise up with vapors and travel towards low pressure area, resulting into cyclonic precipitation. Okay, so again this cyclonic precipitation having two types of precipitation under this frontal and non-frontal precipitation. So this is what the frontal and non-frontal precipitation that is the important topic while we learn this gate syllabus. Okay, so frontal precipitation is nothing but it is a flow of warm air mass into the cold region, and in non-frontal precipitation, that is the cold air meets with stationary warm air, then non-frontal precipitation occurs. Okay, so when the flow of warm air, you can see here, when meets into the cold region, when warm air goes into the cold region, this frontal precipitation happens occurs, and when the cold air meets with the stationary warm air, then non-frontal precipitation occurs. Okay, now the another precipitation type is convective precipitation. So it occurs due to the natural rising of warm lighter air with vapors into the colder and denser region. Now, the third type of precipitation is orthographic. So, orthographic is when heavily moisture laden air stops due to topographic conditions, that is mountains, and precipitations occurs, then it is called orthographic precipitation, just like in Himalaya region. Okay, so you can see, you can imagine, or you can see in the Himalayan region, the orthographic precipitation is happened. Okay, now precipitation due to the turbulent ascent, when the turbulence in the velocity of cloud occurs due to the land surface after long travel on the ocean surface, then there will be rising up of cloud into colder region, and precipitation occurs. Okay, now, what are the characteristics of rainfall? So, first characteristics of rainfall is size and shape. So, the size and shape of the rainfall occurs when the moisture in the atmosphere condenses into drops, and raindrops occurs in any shape up to the approximately 9 mm mean diameter, after which they tend to break up. Now, the second characteristic of the rainfall is intensity and duration. So, amount of water that reaches to ground surface per unit area is called intensity. What is meant by the intensity? It is the amount of water that reaches to ground surface per unit area is called as intensity. Suppose the area is we have is like suppose this is 10 kilometers square. Okay, 10 kilometers square, and whatever amount of water received over this area, the water receives is nothing but the intensity over the particular area of 10 kilometer square. Okay, so that what intensity we have to calculate. Okay, so intensity and the duration are usually inversely related, and high intensity storm are likely to be of short duration, and low intensity storm can have a long duration. Okay, so you can see here, if the intensity is high, so the rainfall is having very less duration or the short duration. If the intensity is very low, then the duration may be high. So this is sometimes it is inversely related to each other. Now we are having the rain gauge to measure the rainfall. Okay, so there are types of rain gauge. So main type of rain gauge which is used to measurement of the rainfall. So first one we are having, that is non-automatic non-recording rain gauge, Siemens rain gauge, automatic recording rain gauge, weighing bucket rain gauge, tipping bucket rain gauge, and float type rain gauge. So these are the main types of rain gauge which is to be used for the measurement of rainfall. Okay. Now we will discuss one by one all the types of rain gauge. So first we will take non-automatic, which is non-recording rain gauge. So these are called non-recording rain gauge because they do not record the rain but only collect the rain. Okay. So in non-automatic or non-recording rain gauge, the rain gauge is only used to collect the rain, and after collection we have to measure by using some formula. Okay, so the collected rain is then measured by means of graduated cylinder, so as to directly represent the rainfall volume in centimeter of water depth. So that is, depth of rainfall or rainwater in centimeter is equals to volume of water collected in centimeter cube and area of the aperture of gauge in centimeter square. Okay, so whatever water is to be collected in particular aperture of the gauge, that volume of the water in meter cube divided by the area of aperture of the gauge in centimeter square, you will give the depth of the rainwater in centimeter. Okay, so what note you have to remember in this non-automatic and non-recording rain gauge is the amount of precipitation or the rainfall is expressed as the depth in centimeter or inches. So whatever the dimension or the unit we have to take for the volume as well as for the area of the aperture, that uh, that unit will decide the depth of rainwater in centimeter or in inches or in meter or in Okay. So second rain gauge is Siemens rain gauge. So you can see here the Siemens rain gauge figure, which shows in the figure 8.1. Okay. Now this is the most common type of non-automatic rain gauge, which consists of cylindrical vessel of having dimension 127 mm, which is nearly equal to 5 inches. Okay, diameter. So you can see here this is the 12 nearly cylindrical vessel. This is the cylindrical vessel, okay, having the 5 inches diameter with the base enlarged to 10, that is 8 inches in diameter. Okay, now the top section is a funnel provided with circular brass rim, exactly 127 mm, that is 5 inches, what we can say, 5 inches internal diameter, and the funnel shank is inserted in the neck of receiving bottle, which is 75 to 100 mm, that is 3 to 4 inches in diameter. So capacity of bottle is 75 to 100 mm of rainfall. The rain gauge is placed in concrete block. So you can see here, this is the concrete block which is in which this rain gauge is placed, and this concrete block is having the dimension of 2 feet by 2 feet by 2 feet. Okay, now the rim should be of 3 not 5 mm, that is 12 inches above the ground surface. So 1 feet of rim is provided on the ground, above the ground surface, and uh, water constraint in the bottle is measured by suitably graduated measuring glass with the accuracy up to zero point 0.1 mm, and during the heavy rainfall the rain should be measured 3 or 4 times in a day. So this is nothing but the funnel. So this is a figure, this showing here, this is nothing but the funnel, This bucket B is nothing but the receiver. Okay, this C is nothing but the body. This is the body. This section is nothing but the body. And D, this is the base. So this is the base. So Siemens rain gauge, which is shown in this figure, you can having the dimension of it. The gate in the gate examination, it might ask about the dimension or uh, uh, part of the Siemens rain gauge. Okay, so this is the non-automatic rain gauge that we have to remember. So sometimes the question may be asked on the true or the false statement, identification of true or false statement about the non-automatic rain gauge, and there will be several options like Siemens rain gauge, non-automatic or non-recording rain gauge. You have to choose any one or any two from this. Okay, so that you have to remember. Now, the measurement of rainfall by an automatic, that is the recording rain gauge. So, in general, automatic rain gauge consists of rotating drum with a graph paper fixed around it. There is open in contact with graph paper, which moves up with the collected rain and thus recording cumulative rain with the passing of time. And these are the three types of automatic rain gauge: weighing bucket rain gauge, tipping bucket rain gauge, and float type rain gauge. So we will see one by one. So first we will see the weighing bucket rain gauge. So weighing bucket rain gauge consists of a receiver bucket supported by a spring or lever balance or any other weighing mechanism. The movement of bucket due to its increasing weight is transmitted to a pen which traces the record on a clock driven chart. So you can see here, this is the receiver bucket, okay, which is placed on the pan. Okay, now here this pan is attached to this weighing mechanism, and whatever the weight of the receiver bucket, after getting the rainfall into it, the pen arm will the record draw on the record drum how much is the rainfall. Okay, so in this graph, the values are given, and on the particular value, looking into the weight of that receiver bucket, which is measured in the weighing mechanism, due to that the pen arm will draw on a particular uh, what we can say, the value of the rainfall. Okay, now, this is the another type of automatic rain gauge, that is the tipping bucket rain gauge, which consists of 30 centimeter diameter sharp edge receiver, and at the end of the receiver funnel is provided. Under the funnel, a pair of bucket are pivoted, the central point which balances in such a way that when one bucket receives 0.25 mm, that is 0.01 inches of rainfall, it tips to fall or turn over, discharging its contents into reservoir, bringing other bucket under funnel. Now, tipping of bucket completes an electric circuit, causing the movement of pen to mark on clock-driven revolving drum, which carries a record sheet. So you can see here in the figure, the figure shows the tipping bucket, the arrangement of tipping bucket rain gauge. So you can see here the receiver is having the 30 centimeter diameter, which we can see here. Okay, now this receiver receives the water, and which at the end the receiver funnel is provided. Okay, now from this funnel, a pair of bucket are pivoted, that is the central point of which balance. Okay, and and it is situated, or it is placed in such a way that when one bucket receives 0.01 inch of the rainfall, it tips. Okay, and this uh, contents into the reservoir, bringing other bucket under the funnel. Now, this tipping of the bucket completes an electric circuit, which causing the movement of pen. You can see here. Okay, and this pen is used to mark on the clock driven revolving drum which carries a recorded sheet. Okay, so you can see here this is the stationary magnet on frame, this is the pivot bar, so this is magnet. Okay, so as rain fills up one side of the tipping bucket, the weight of the water causes the seesaw to tip over and dump. The magnet on the tipper passes the stationary magnet, sending a current to a transmitter below. Okay, so here you can see the arrangement of tipping bucket rain gauge. This which is one of the automatic rain gauge. Now you can see here in figure 8.3 the tipping bucket rain gauge in actual. Okay, in the first, this is the graphical representation of the tipping bucket rain gauge, and you can see in the figure number 8.3 you can see the actual tipping bucket rain gauge. You can see here is the rim. Okay, this is nothing but the collector, this is the tipping bucket. Okay, this is the contact. Now this tip, okay, which is placed over the stand. Okay, so this is what the diagram of or the figure of tipping bucket rain gauge. Now the third type of automatic rain gauge is float type rain gauge. So float type rain gauge, which is working similar to the weighing gauge bucket, in which the funnel receives the rainwater which is collected in rectangular container. Now float is provided at the bottom of the container. You can see in the figure itself. Okay, this is the float which is provided at the bottom. Now float is raised as the water level rises in the container. Okay, so this is the container. Okay, now movement of float is being recorded by a pen moving on a recording drum actuated by clockwork. When the water level in the container rises so that float touches the top, the siphon comes into operation and release the water. Thus, all the water in the box is drained out. Okay, so you can see here the siphon is provided at this moment. Okay, the funnel is provided at the top of this. Water is collected through this funnel and this container is getting filled with water. As the water is getting increases, this float will go up, and due to which this float is attached with this float rod, and this float rod is attached with this pen arm. Okay, which is recording the uh, readings on the drum. Okay, so whenever the water is increases, this float will uh, goes upside. Okay, wait a minute. Just wait a minute. चलो ठीक. Am I audible? Okay, I hope I am visible, audible, and my screen is visible to everyone. Okay. Now moving towards the flow type rain gauge, which is the automatic rain gauge, in which you can see here the funnel is provided at the top of this container, which collects the water and uh, drop that water into the container. And as the water is raises in this container, the float will raise. Okay, and due to which this float rod will disturb this pen arm, and this pen arm will write down all the readings on the recording drum. Okay, so uh, at this is the procedure which adopted in this float type rain gauge. Okay, now what are the advantages of recording gauge over the non-recording gauge? So in recording gauge, rainfall is recorded automatically, and therefore there is no necessity of any attendant. Recording rain gauge gives the intensity of rainfall at any time, while the non-recording gauge gives the total rainfall in any particular interval of time. So no attendant is required. Such rain gauge can be installed in far off places also, and the possibility of human error is obviated. So no doubt the recording rain gauge is far better than the non-recording gauge. Now, what are the disadvantages of the recording gauge over the non-recording gauge? So, no doubt it is costly. Okay, so it is costly in comparison with the non-recording gauge, and the fault may be developed in electrical or mechanical mechanism or recording the rainfall. Okay, so there may be a mechanical error, electrical error, which can be produced in the gauge. Okay, now, we will move to the next topic, that is the computation of the average rainfall over a basin. So, in order to compute the average rainfall over basin or catchment area, the rainfall is measured at a number of rain gauge stations suitably located in the area. The number of rain gauge stations depend upon the area and the distribution of rainfall. If a basin or catchment area contains more than one rain gauge station, the computation of average rainfall may be done by the following methods: arithmetic, arithmetic average method, Thyssen Polygon method, and Isoheital method. So these are the three methods through which we can calculate the average rainfall by providing more than one rain gauge station over the basin or the catchment area. So how we have to calculate the average rainfall, that we will see one by one. So first we will see the arithmetic average method. So on the basis of this arithmetic average method or Thyssen Polygon method or Isoheital method, the question may be asked in the gate examination. So this is arithmetic average method is the simplest method of estimating rainfall, average rainfall. Average rainfall is calculated by arithmetic average of recorded rainfall at various stations. If P1, P2, P3 and up to Pn are the rainfall values measured at n number of gauges, we have equation as P average is equals to P1 plus P2 plus P3 plus up to Pn divided by number of rain gauge station. Okay, and directly we will get the average rainfall. Now, what are the advantages of this? So this is suitable method when rainfall is uniform. So in the case of uniform rainfall over the basin, this is the method which can be adopted. Now, example of this is using arithmetic average method, find the average rainfall over the catchment. The rain gauge data is 12.6, 8.8, 14.8, 10.4 and 16.2. So there are five number of rain gauge station, and all that five rain gauge stations are collected uh, the rainfall is 12.6, 18.8, 14.8, 10.4 and 16.2 mm. So what we have to do, we have to use the arithmetic equation as P1 plus P2 plus P3 plus P4 plus P5 divided by 5. Okay. So by doing all these, by putting all these value into the equation, we will get the average value as 14.56 mm. So average rainfall at but that particular basin through that 5 rain gauge station, we will get as 14.56. Now move towards the another method of calculating the average rainfall, that is the Thyssen polygon method. This method is more common method of weighing the rain gauge observation according to the area, which is also called as weighted mean method. Now, which is accurate than the arithmetic average method, and average rainfall can be computed by the following expression. So this equation is having uh, P average is equals to P1 A1 plus P2 A2 plus P3 A3 plus Pn An up to the number of station into the area divided by A1 plus A2 plus A3 plus An. So the advantages of this method is based on the assumption that a rain gauge station best represent the area which is close to it. Now, suppose we are having this much of area, okay, and we have provided A station, B station, C station, and D station. Now, A rain gauge station is having this much area, okay. So A will be responsible to collect this much rainfall of this much area. B station will be responsible to collect the rainfall at this much area. Okay. Now C rain gauge will be responsible to collect this much rainfall at the particular area, and lastly the D station railway gauge rain gauge station will be responsible for this much of area. Now the whole area is divided into four stations, and you will get the average rainfall from this uh, station 1 having whatever the rainfall multiply the area plus station B is whatever will be the rainfall multiply the area 2 or area B. Similarly, area C with the rainfall, area D with the rainfall divided by whole area. So you will get the average rainfall on the particular area. So in this statement, it is written as the join the adjacent drainage station, construct the perpendicular bisector of each of these line. The polygon formed by the perpendicular bisector around a station encloses an area which is everywhere closer to that station than to any other station. Find the area of each of these polygons shown hashed in the figure. Compute the area average precipitation using the given formula. Now, the example on it is example of using Thyssen polygon method. Find average rainfall over a catchment. The data is rain gauge station A, B, C, D, E are given, in which the polygon area in kilometer square is 40, 45, 38, 30, 43, and precipitation in mm is 30.8, 33.4, 34.6, 32.6 and 24.6 respectively. So what we have to do, we have to do in the solution, we have to prepare a table in which In the table, first column consists of rain gauge station A, B, C, D, E. Then the second column consists of polygon area in kilometer square. Then precipitation in mm, and then A into P. Because in equation we having A into P divided by A into P divided by A. So ultimately, when we multiply this column 2 with column 3, you will get this column 4 kilometer square into mm, and you will take the sum. Uh, you will sum this value and make this as 6085.6 and divide this value with this 193. You will get the average rainfall in the particular area. Okay, so um, the last method of the average rainfall is isoheital method. So an isoheight is a line on a rainfall map of the basin joining places of equal rainfall readings. An isoheital map showing contours of equal rainfall presents a more accurate picture of the rainfall distribution over the basin. Now, average rainfall can be computed by the following expression. So, this is given by the equation as P average, that is rainfall average, is equals to sum of area into P1 plus P2 divided by 2 divided by sum of area. So the advantages of isoheital method is the most elaborate and accurate than other two methods. Okay. Now what is the procedure of this is the area is divided into these lines. Okay. So what we have to do is from the rainfall value recorded at various rain gauge station, prepare the isoheital map. Measure the area enclosed between the successive isoheight with the help of planimeter and multiply each of these area by the average rainfall between the isoheight, and these compute the average rainfall applying to the given formula. So these are the number of rain gauge station, okay, which gives the value of rainfall. Now we have to draw this isoheight line with respect to the rainfall we receive through this rainfall gauge station, and we have to divide this isoheight line into the number of area. Okay, now this isoheight will be divided into the sum of the area. You will get the average rainfall um, uh, through this isoheight method. Okay, now we will see the example of this. Using isoheital method, find average rainfall over a catchment. The data is given as isoheight is 12, 13, 14, 15, 16, and 17 centimeter. Now area between the isoheight in kilometer is 22. The isoheight of 12 and 13, in between that there is a area of 22 kilometer. Isoheight line between 13 and 14, there is a area in between 80 kilometer per square. 14 and 15 isoheights between in between 110 kilometer area is kilometer square area is there. So 15 centimeter and 16 centimeter isoheight line having the area 89 kilometer square. 16 and 17 centimeter line isoheights line having the 70 kilometer square area. Now average precipitation is 12.5, 13.5, 14.5, 15.5, and 16.5. So whatever value we are getting at this stage, we have to multiply this 22 with 12.5 and divide this value with 371. Okay, so if you will get the product of a into p plus p1 plus p2 divided by 2, you will get 5484.5, and that is divided with 371, so you will get the p average as 14.78 centimeter. Now this is how we have to calculate the average rainfall through this isoheital method, through this Thyssen method, and through this arithmetic average method. Okay. Now, the last topic of this today's lecture is We have to find out the mean precipitation for the area sketched in the figure by Thyssen method. The area is composed of a square plus and equilateral triangular plot of side 4 kilometers. Rainfall readings in centimeter at the various station are also given in figure. So the data is given as you have to calculate uh, the average precipitation or the average rainfall through the Thyssen method. Okay. Now, presentation of rainfall data. A few commonly used method of presentation of rainfall data which have been found to be useful in interpretation and analysis of such data are mass curve of rainfall, or second one is hydrograph. Okay. Now, what is meant by the mass curve of rainfall? If the total accumulated precipitation is plotted against time, the curve obtained is known as mass curve of rainfall or storm. The curve rises steeply in the beginning and then tends to become constant. Mass curve of rainfall are very useful in extracting the information on the duration and the magnitude of the storm. Also, intensities at various time interval in a storm can be obtained. Now, in case of hydrograph, it can be defined as the plot of intensity of rainfall centimeter per hour against the time interval represented as a bar chart. The area under hydrograph represents the total precipitation received in the period. This chart is very useful in representing the characteristics of storm and particularly important in developing the design storm to predict extreme floods. The time interval used depend on the purpose. In urban drainage problem, small duration are used, while in flood flow computation in larger catchment, the interval are of about 6 hours. So, what is the precipitation estimating point rainfall? In estimating point rainfall, the method of weighted average is often used. This gives depth of rainfall that is smaller than the greatest amount and larger than the smallest amount of the area. That is lies between P maximum and P minimum of the area. Now, what is mean by the estimating point rainfall? The method of this is consider that rainfall is to be calculated for point A. Establish a set of axes running through A and determine the absolute coordinate of nearest surrounding point B, C, D, E, F. The estimated precipitation at A is determined as a weighted average of the other 5 points. The weight are a reciprocal of the sum of squares of del x and del y. That is d square is equals to del x square plus del y square and w is equals to 1 by d square. The estimated rainfall at the point of interest is given by sum of P into W divided by sum of W. Now, the example is given for determination of rainfall. So here you can see the point A, B, C, D, E, F are given, in which the rainfall are given for B as 160 mm, C is 180 mm, D is 150 mm, E is 200 mm, and F is 170 mm. Now del X value is having 40, 10, 30, 30 and 20 in meter, where del Y value is 20, 16, 20, 30 and 20. So in the next column, what we have to do, we have to sum of this del X square plus del Y square. Okay. Now we have to calculate this D. This D is calculated through this del X square plus del Y square. Okay. Now we have to calculate then W. So W is calculated uh, W is calculated through the equation sum of P into W. Okay. So how we have to calculate the or how we have to estimate the precipitation of A, that is sum of P into W divided by sum of W. Okay. So that is what the example is given. Now the method in the theory part is given as draw x and y axis through the interested point, mark up the distance along the x and y axis, put them down distances along the ordinates, calculate d square is equals to del x square plus del y square, calculate w as 1 by d square, have the sum p into w, that is sum of p into w, and rainfall at the point sum of P into W divided by sum of W. So this is what the procedure to calculate this estimated precipitation at A. Okay. Now the next is the aerial precipitation. So for most hydrologic analysis, it is important to know the aerial distribution of precipitation. Usually the average depth for representative portions of the watershed are determined and used for this purpose. The most direct approach is to use the arithmetic average of the gauge quantities. The procedure is satisfactory if gauges are uniformly distributed and topography is flat. So other commonly used methods are Isoheital and Thyssen method. So aerial precipitation is having the another method like Isoheital method. Already we have seen the Thyssen method. We already seen. Okay. Now the reliability of rainfall measured at one gauge in representing the average depth over a surrounding area is a function of the distance from the gauge to the center of the representative area, the size of the area, topography, the nature of the rainfall of concern, storm event versus mean monthly or the annual, local storm characteristics. Now, at this moment, we will stop here because the next topic we have to cover, which is the part of the gate examination. Okay, so so we will solve the numerical which is asked in the gate examination about the hydrology. Okay. So this type of question is asked in the gate examination for hydrology and irrigation. So this question is asked uh, from the uh, gate question paper, and the rainfall of 5 successive days in a catchment were measured as 3, 8, 12, 6, and 2 centimeter. If the total runoff at the outlet from the catchment was 15 centimeter, the value of the phi index in mm per hour is. So we have to calculate the phi index value, and the options are given as 00, 1.04, 1.53, and sufficient information is not available. So you can see here the runoff, total runoff is given as 15 centimeter, and by the observation runoff above 6 centimeter is 8 centimeter, runoff above 3 centimeter is 13 centimeter, you can see here. Okay. And runoff, so 15 is in between 3 and 6. Okay, so 8 plus 6 minus 5 into 3, we will get the value as 15. So 5 is unknown here, so 3.667 centimeter per day if you have to calculate, and then you have to convert this into centimeter per hour or mm per hour, so you will get the value as 1.53 mm per hour. So option number C will be the right answer for this. So this kind of question is normally asked in the gate examination, which we have covered in the theory as well. Now, the during 6 hour storm, the rainfall intensity was 0.8 centimeter per hour on a catchment of the area 8.6 kilometer square. The measured runoff volume during this period was 2 lakhs 56,000 meter cube. The total rainfall was lost due to infiltration, evaporation, and transpiration. So these three things we have to calculate. So volume of water is nothing but the area into depth. Area is given as 8.6 kilometer square. We have to convert this into meter by multiplying 10 raised to the power 6, and the depth is given as 0.8 into 6 hour divided by 100, and you will get the volume of water as 4 T1 for 4 lakh 12,800 meter cube. Now runoff volume is having 2 lakh 56,000 meter cube. So loss of water will be 4 lakh 12,800 minus 2 lakh 56,000. You will get the value as 1 lakh 56,800 meter cube. Now you can use the equation of if you have to calculate in terms of depth. So volume lost divided by area. So you will get 0.304 centimeter per hour. So option number B will be the right answer for this. So like this, you have to calculate the depth of rainfall, okay, per centimeter per hour. Okay, now the next, the question asked about the plan area of the reservoir. This is the question is asked regarding the catchment area. So the plan area of the reservoir is 1 kilometer square. The water level in the reservoir is observed to decline by 20 centimeter in a certain period. During this period, the reservoir receives a surface inflow of 10 hectometer and 20 hectometer are subtracted from the reservoir for irrigation and power. The pan evaporation and rainfall recorded during the same period at a nearby meteorological station are 12 centimeter and 3 centimeter respectively. The calibrated pan factor is 0.7. The seepage has from the reservoir during the period in the hectometer is, the options are given as 0, 1, 2.4 and 4.6. So the data, as per the data given, inflow of water is given 10 into 10 raised to the power 4 meter cube. Outflow is given as 20 into 10 raised to the power 4 meter cube. All the data you have to convert into meter or in centimeter. Okay. Rainfall is 3 centimeter. Volume of rainfall is 1 into 10 raised to the power 6 into 3 by 100. This 3 we have to convert into meter. So we will get the value 3 into 10 raised to the power 4 meter cube. So evaporation is done 0.7 into 12. So 8.4 centimeter. Volume of evaporation is 8.4 divided by 100 into 1 into 10 raised to the power 6. So 8.4 into 10 raised to the power 4 will be the volume of evaporation. Now net decrease of the volume is 10 minus 20 plus 3 minus 8.4 into 10 raised to the power 4. So you will get minus 15.4 will be the decrease of the volume. So in terms of depth, minus 15.4 into 10 raised to the 4 divided by 10 raised to the 6, you will get the value as minus 15.4. Okay, so seepage will be equals to 20 minus 15.4, 4.6. So option D will be the right answer for this. Okay, so likewise, you have to solve the question which is asked in the GATE examination. And at this moment we will stop here, and same topic we will having in the extension of this hydrology, we will having the next topic. We will see that topic in the next class. Okay, so till then, thank you very much.
थैंक यू सो मच सर, shall I end the video?
नीरज सर, आप इसको स्टॉप कीजिए अभी का, और एक 10-15 मिनट में अपन एक कंटिन्यू क्लास ले लेंगे या कल लेंगे?
सर मैं आपको बताता हूँ कौन